Hello. Welcome to Lesson 4. In this lesson, we will talk about the patterns and generalization of a problem's solution. This is the continuation of the problem-solving lesson. Slide 2. This lesson duration is about 75 minutes. We organize the trainees to a group of maximum 15 persons. For the lesson we will need a projector, a questionnaire and a personal computer or laptop for the trainees. The objective aim of this lesson is to show the benefits of generalizing from patterns in problems as well as techniques for creating them. Effective problem solving actually involves more than just finding a solution. Once we've found a solution, we should put effort into its improvement by finding ways to make it more powerful. Recognizing and exploiting patterns is a crucial early step in this process. Why look for patterns? As we analyze a problem and begin work on its solution, we'll probably notice that some elements repeat or are at least very similar to one another. If we don't automatically notice the patterns in a solution, we should make an effort to seek them out because they are the first step to making our solution more manageable and powerful. As an example, consider automating the drawing of complex shapes and images. The idea of a shape is rather abstract. Just think how many varied types of shapes and patterns exist. To gain a foothold on the problem, we could take a smiley face and think about how to solve that single example. By combining this strategy with decomposition, we might find we could draw a smiley face by breaking it down into several simpler shapes, which are each easy to draw. 1. A circle, to serve as the head. 2. Two concentric circles, the smaller one of which is solid, which make eyes. 3. A curve, which makes the mouth. The solution for this one example points the way to a general solution. Any complex, unfamiliar shape can be considered as being made up of several simpler, familiar as we can see on the next image. In the previous slide, we saw an approach to drawing a simple image of a face. This approach broke the image down into simpler, elemental shapes that could be positioned and drawn easily. The algorithm that draws such an image might therefore look like this. 1. Draw circle with radius 30 at position 50,50 with line thickness 2. 2. Draw circle with radius 6 at position 40,40 with line thickness 1. 3. Draw circle with radius 3 at position 40,40 filled black. 4. Draw circle with radius 6 at position 60,40 with line thickness 1. 5. Draw circle with radius 3 at position 60,40 filled black. 6. Draw red line from position 30,70 to position 70,70 with line thickness 1. In this example, the patterns across instructions should be fairly simple to spot. The emergence of a pattern provides an opportunity for improvement. Instead of them being disjointed and separated, those parts making up the pattern can usually be brought together and solved using a common approach. In other words, we can take some separate, but similar concepts, and generalize them into a single concept. As a result, the solution becomes simpler because it contains fewer distinct concepts, and it becomes more powerful because we can reuse it in other situations and solutions. Recognizing simple patterns. Here's one approach to spotting simple patterns. Look for nouns that appear repeatedly. These could correspond to objects that your solution deals with. Look for verbs that appear repeatedly. These could be operations that the solution carries out. Look for concrete descriptions. These could probably be substituted by placeholders that vary in different situations. For example, adjectives, red, long, smooth, which indicate properties of things and could be replaced by the property name, color, size, texture. Actual numbers, which could be replaced with variables. Let's illustrate all this by examining the algorithm above. What patterns can be seen? Nouns like circle, radius, position, line, thickness. Verbs like draw. Adjectives like red, black, filled. Numbers in several places. Looking at the nouns, we see that some of them translate into objects, circle and line, while the rest are properties of those objects, radius, position, line thickness. line and circle are specific instances of shapes. Hence, shape is a generalization of line and circle. The verbs are straightforward, there's only one. Drawing appears to be a fundamental operation in this solution. Operations often need supplying with things to work with. Data given to an operation when it is triggered is called a parameter. In this case, drawing doesn't make any sense without having a shape to draw, so the draw operation should be given a shape parameter. The adjectives red and black are specific cases of the more general concept of color. The word filled, being derived from a verb, actually suggests another operation which we could formalize, filling a shape with a color. Such an operation would then have two parameters. All the numbers match up with object properties. In other words, these properties, position, radius, thickness, have values that can vary. The generalizations that have been extracted can be seen below. 1. Draw, shape, an operation that renders a shape. 2. Fill, shape, color, an operation that makes the interior of a shape solid with a color. 3. Shape, a form with an external boundary. Specific shapes include, a. Circle, a type of shape with a radius, position and a line thickness. b. Line, a type of shape with two positions, aka coordinates, and a line thickness. 4. Color, red, blue, green and so on. To summarize what has been done so far, we took a concrete solution, looked for patterns in it and simplified them. The original solution was a specialization, capable only of drawing a specific shape. The generalizations taken from it form the core concepts of not only the original solution but any solution that involves breaking down a complex image into simple parts. The solution is not perfect, it could benefit from improvements. For example, line thickness is not, mathematically speaking, a property of a shape. What's more, in our example, line thickness doesn't vary much between individual shapes. We could improve this by introducing another concept called pen, which is responsible for the appearance of the shape's boundaries. Line thickness would instead belong to the pen, and it could be changed in between drawing each shape if need be. More complex patterns. Looking for larger and more complex patterns requires you to expand your scope because you'll need to consider whole groups of instructions at once. It can be harder and will take some experience getting used to, but it's worth it because you can put those patterns to work in powerful ways. In brief, the guidelines for some of the more complex patterns are: 1. Patterns among a sequence of instructions can be generalized into loops. 2. Patterns among separate groups of instructions can be generalized into subroutines. 3. Patterns among conditionals or equations can be generalized into rules. Loops. Looping is the execution of the same series of steps repeatedly. This is a type of generalization. In order to roll a sequence of steps up into a loop, you need to look at their specific forms and then derive one general form. A block of instructions that appear very repetitive usually gives the game away. For example, consider this block. Draw circle with radius 6 at position 40, 40. Draw circle with radius 3 at position 40, 40 filled black. Draw circle with radius 6 at position 60, 40. Draw circle with radius 3 at position 60, 40 filled black. We see a pattern here. Together, the last two steps essentially repeat the first two, only with a slight difference in positioning. We could therefore put these steps into a loop. 1. Let coordinates equals 40, 40, 60, 42. For each coordinate x, y do the following. A. Draw circle with radius 6 at position x, y. B. Draw circle with radius 3 at position x, y filled black. In this example, the steps in the loop should be executed for each pair of coordinates. So, we set up a list of coordinates and use that as the controlling variable of the loop. Put into words, the loop essentially says, for each coordinate carry out the following steps, where the coordinate values in the current iteration are represented by x and y. In the first iteration, x equals 40 and y equals 40. In the second iteration, x equals 60 and y equals 40. This generalization makes the solution more flexible. If we want to draw more eyes in different places, we simply add more coordinates to the list and the loop takes care of the rest. Alternatively, we could draw a cyclops by lopping off a coordinate. Subroutines. The next type of generalization concerns patterns among separate blocks of instructions. Imagine that we are drawing several faces. In this case, those two steps would be repeated in several different places. But then imagine you wish to alter the way you draw eyes, maybe by giving the iris a larger radius. You would have to update the steps in all those different places. Instead of that, we could apply a generalization that not only keeps the definition of an eye in one place but also saves time when first writing the solution. As a reminder, a concrete example of drawing an eye looks like this. Draw circle with radius 6 at position 40, 40. Draw circle with radius 3 at position 40, 40 filled black. A generalized version might therefore look like this. Draw circle with radius R1 at position X, Y. Draw circle with radius R2 at position X, Y filled black. We could then declare that these steps constitute a subroutine, that is to say, a sequence of instructions that perform a distinct, often invoked task and which can therefore be packaged as a unit. It would look something like this. Draw eye is a subroutine which calls the draw circle with radius R1 at position X, Y and draw a circle with radius R2 at position X, Y filled black. Rules. The drawing routines defined in the previous slide contain a pattern we have not yet picked out, although we might have spotted it already. When drawing an eye, the radius of the inner circle is always half the radius of the outer circle. If that is indeed the rule, then we can encode it explicitly into the subroutine so it becomes: draw eye is a subroutine, R, X, Y. Draw circle with radius R at position X, Y. Draw circle with radius half R at position X, Y filled black. In addition to equations, conditionals are a good identifier of rules. Rules are normally indicated by words like when and unless, as well as patterns like if-then. For example, if a circle is not filled with a color, then it takes on the background color - this is a rule that has been implicit in drawing every circle so far. Lesson activity. The trainer shares a sheet with 2 exercises. Trainees, write down the answers for the next 20 minutes and at the end they all together discuss the results. The discussion follows last 10 minutes.